Okay, gamers, welcome. Today, what we're going to do is create a Vulkan renderer from scratch that can render 1 million instances of something. That's going to be the challenge. So let's make a Vulkan, not Vulkan vid, Vulkan Chad. Okay, guys, Vulkan Chad, because not every Vulkan renderer can render so many instances. So let's have a chad.c. And let's get to it, because like we have a timer of 2 hours. I hope you can see it. And yeah, we're really constrained to that. So, and okay, that's also a problem. I cannot press Alt H to open a terminal. So let's go into dev slash chat, Vulkan chat, and make a gcc-o chat.c chat. Oh no. Oh fuck, we overwrote our file already. Okay, we need to do it like this. Yeah, so chat, nice. Next thing, including Vulkan headers. So let's include the Vulkan headers, and let's have something like a function, create instance. And it should take in our context, right guys? Let's have something like a type def struct chat context, and our chat context definitely should have a vk instance, and we're kind of forced to pass the chat context. Okay, so a vk create instance needs a vk instance create info. In Vulkan, every object needs a create info in which you can pass all of the parameters. For example, yeah, p application info is a const vk application info, which we need to pass into here, and then we can specify some info. So let's pass that like this, and this is info, and this, let's call this like something like create info, and this app info. Application version, it's, I don't know. I think there's this thing, vk make version. Yeah, let's just have 9.9.9, or better yet 4.2.0. API version, I think this is actually the API version we need of Vulkan, so I think we should also use that. So we want Vulkan version 1.4.0, but I'm not sure. I think there's something like vk API version. This. Okay, they do it like that. Then I think this is just a better way to just do that, right? Application version, we already have that. So engine version, I mean, yeah, it's, I think this is like very unnecessary. I don't know why Vulkan is so high level in this app info thingy, because after this struct, everything is like so low level that something like engine name, let's call it Chad engine. Application name 1 million chads. S-type. S-type is also a thing. It's a structure type, and we need to specify it for every structure in Vulkan. So this P next, we don't need that. API version, application version, engine name, application name. Okay, so we already specified everything. So let's pass app info. Flags, I don't think we need flags, but this is pretty important. This is actually pretty important. What we will need, enabled layer count. What we will probably need is something like let's just put that in the context. So let's have a const char pointer layers, extensions, UN32T, N layers, and N extensions. That's going to be the Vulkan extensions and Vulkan layers. For validation layers, for example, we need a validation layer flag. And for the extensions, we're just going to query GFW for all of these supported extensions. So, enabled layer count will be context.n layers. Enabled extension count, context.n extensions. Enabled layer names, context n layers. EP enabled. Oh wait, it's a double pointer, right? Isn't it? Enabled layer names is a double pointer. Extensions. Ah yeah, I think it is a double pointer because obviously we kind of need a char, like a pointer of char pointers. Let's just have it like this. Okay. Application info, and then I think we only need the S type. VK structure type instance create info. Okay, and then we create the instance with the create info. Allocator, we'll always have the allocator null. P instance is context.instance. Ext. And here we just no, we don't even return anything. I think we could do something like if not equal VK success. And I'm not going to be very cautious about writing perfect code, returning correct values, creating a log system or something. Because like this will just take very long time. And then we just exit with 1. Okay, so why can't I? Let's just quickly go to Firefox and GFW. Just copy the example program. Like that. And say GFW/GFW3.h. And then we don't need this, we don't need this. Swap buffers. I think this is also an OpenGL feature, but let's just keep that for now. Okay, let's have it named 1,000,000 chats. Okay, then there's a function called GFW get. Oh my god, my autocomplete doesn't work. Need to reopen. GFW gets required instance extensions. Returns the count and instances and extensions. And this is basically our const char pointer exts, and then we can have our const char pointer layers is equal to, and then we need the KHR validation. Isn't there a Vulkan info? Yeah, I already did that. Perfect. So exactly this one. Okay, we are 10 minutes in, so let's create the thing, create instance, and let's have a struct. It's not even struct, we can just do it like this. CTX, and then CTX.nexts is equal to nexts, CTX.n layers equal to 1, CTX.exts is equal to exts, CTX.layers is equal to layers, and then we create the instance with context. And I think we should, because I cannot see us not doing that, we could kind of need a system like this, where we don't just exit mid-functions, or just in general don't exit in functions. And then like, if not, exit 1. But let's try that. This should create the instance, right? Nice. So we have a Vulkan instance. Okay, so the next thing we need to do is to create the Vulkan surface. And I think there's a GFW thing, GFW, but let me check that. We kind of need to do something. Vulkan, yes, this. I think it's this. So we need to do that so that GFW acts as a correct Vulkan thing. And what we then need is to create a Vulkan surface. So create Vulkan surface. And the surface is a VK-KHR, VK surface KHR surface. And yeah, and we need to create that. So let's create the surface with the instance or with the context in general. So let's have chat context. Let's just say void, and we'll just say create. We also need a window, so let's just add that because GFW creates window surface. GFW create window surface. I'm pretty sure it's called like that. Yeah, here GFW create window surface, and GFW include Vulkan doesn't work or what? That's bad. Maybe we need to like include it at the top or something. Maybe it's just my autocomplete, but context.instance surface. Ah, now it works. Oh, perfect. Context.win null context.surface. And then we can check if context.surface, if not, we can bool in here as well and say fail to create Vulkan surface. Count false, return true, cd error, cd out, create the Vulkan surface. So this is basically the next step, and we'll see the steps in the log then, which is pretty nice, I guess. And then for this, we just replace with window with context.win. Okay, that's kind of not that good. Okay. So after this, if not, creates Vulkan surface context exit 1. This is basically oh my god. This is basically the surface that Vulkan will render to, because you could theoretically also create a surface in like DRM or like with other windowing systems. So this is the abstraction here basically. Context.instance, context.win, null context.surface. Okay, that's weird. I think what we need to do, yeah, that's very important. After initializing Vulkan, we need to say GFW window hint, GFW client API, GFW no API. Because when we don't do that, then the this function, which is a Vulkan specific function, will not work because GFW thinks we are using OpenGL. Created Vulkan service, perfect. And now GFW swap buffers doesn't work anymore, and you can see that our window is like kind of yeah, how should I say it, kind of like fucked up, I guess. So we need to create a swap chain now. Okay, so the first thing we need to write is a function to pick a physical device, which is basically a GPU. So it's a VK physical device physdef. And what we basically want is a static bool pick first stuff. And it takes in a chat context CTX. And we need to enumerate the physical devices. Basically, it returns us all of the physical devices, all the GPUs that Vulkan found. So let's name it like nfistef. nfistef. And then we'll do null in here and do the same thing again with nfistef and vk physical device defs, and then like something like, I don't know how many GPUs will you have, 8 or something? I mean, 8 GPUs is kind of insane, but okay. We'll support 8. Because psychopaths with 9 GPUs, I mean, no. We won't support that. And then we just pass defs. And yeah, and then what I wanted to do is check if nfistef is equal to 0. Then we want to return false and say that we didn't found any GPUs that support Vulkan. So chat, we didn't find any GPUs that support Vulkan. Okay, and then we just go through the GPUs, ISS and nfistef, I++, and then we get the def is equal to defs.i. And then we basically want to check if they support, like this, like the GPU supports presenting queue and a graphics queue. So presenting queue is basically getting the picture onto the screen with a swap chain and all of that. And the graphics queue is the rasterizer basically. And stuff like that. Don't quote me on that, I'm not a Vulkan expert, but this is basically the idea. So what we want to do is get a something like a, yeah, what's the function name? vk get. Let's first check the function. Get physical device queue family properties. I think this returns the context.fistef. No, it's context.instance. Or no, it's not. So we need def. I'm sorry, def. And okay, then this is what I wanted. So queue count. And queue family properties will be null at first, because we first need to retrieve the count and then do the same thing with the families. So vkq family properties props, we pass, yeah, we can actually pass nfistef. No, we this doesn't make sense, because like theoretically, like the queue families per device have nothing to do with how many devices you have, right? So yeah, let's do that and pass props. And then we can iterate the queue family properties and check if both graphics queue and a present queue is present. So for j is equal to 0, j is less than queue count, j++, and then we just check if props at j, that's important, when props at j dot queue flags has vkq graphics bit. This is how you check if a device has a graphics queue. Then we can already check. Yeah, how we basically want to get the U-entity graphics queue family index is 0, or it's like actually -1, because theoretically, what if we didn't found any? Present queue family index And then we say graphics Q family index is equal to I equal to J. And yeah, and then what we kind of also need to check is if we also can present. So we kind of need to check if the physical device supports presenting to the surface that we got from GFW. So VK get physical device surface support. GHR. It's actually not a function pointer, it's just the actual function. With the def J context.surface and then a, what is it, a VK rule 32 supported is equal to false, or I think there's VK false, and then and supported. And so basically if we are able to support presenting with that device to our surface, we say present Q family index is equal to J, and if yeah, and this is basically the only case. So support that. So we can check if the graphics Q family index is not equal to -1 and the present. So basically we found both Qs on this device. Then we say something like context.physdef is equal to the device and context dot, and then we will need to store those families because we will need them later. So int32t graphics Q family index present Q family index. So graphics Q family index is graphics Q family index. This is present okay, and then we just return true. What we could do is actually log and return false in here. So did I do everything correct? I mean, it could theoretically say if graphics Q family index does not equal -1, then we can break out of that for loop, because that means that we found both. And yeah, and this is like this, and yeah. What I wanted to say is that we can get the VK get physical device properties, I guess, from the device, and VK physical device properties props, and then we can say something like fprintf s3 out chad picked physical device, and then we can say something like name %s, and I think API version %s, and driver version and stuff like that. Driver version %s, I think that's it. I mean, we don't really need any more things, and this is kind of a time waste. So vendor name or device name, props.api version, props.driver version, right? This is obviously not a S. I think we even need to VK make version. Use of undeclared. What? VK make version? VK make version. I don't think so. No. Yeah. I don't know if there's a backward thing. Yeah, let's just print that, and then in here let's say std error failed to pick physical device. Okay, like this. and then say if not, pick physdef with context, we exit with 1 as well. Okay, so let's try that. I think it worked. Like, or did it? I mean, it kind of. What the fuck? Why didn't it print anything? I mean, that's not even possible. Pick physical device. We didn't find any. So, in every return case, we print something. Right? I mean, theoretically, like the breaking may be scuffed. I mean, we can check that. What? Pick physical device? That's extremely weird. I mean, let's printf something. Okay, this works. And something like in here. Still works. And here. And here we just don't get anything. But, so you want to tell me that... But I mean... We kind of needed to get here. Ah, did I forgot a \n or something? Yeah, bruh. This was a not so valid time waste. Oh, perfect. So this is my GPU. GPU leak. GPU leak. Okay, so I'm ticking off my list. So I think the next thing. Let me see. The next thing we need to do is create a, I think a logical device, yes. So, creating Vulkan logical device is kind of scuffed it out. So, a logical device is basically like the OpenGL context, you could say. So, because you pass the logical device to every Vulkan call, and yeah, because like you pass the logical device to every Vulkan call, and it's just basically your core structure. Okay, so the basic function that we will need to call is vk create device. Vk create device. This is a bool. And vk create device takes in a physical device, that's why we needed to pick that, and a create info. So a const vk device create info. Device info is equal to, and here you see it again, they all take in the info struct, so it's always the same. So the device info, we need to specify queue create infos, yeah, and then yeah, this is like very weird. So, what we basically want is a vk device queue create info, queue infos, and we can have 2 maximum queues because we only have present and graphics, and we got them, so we can check. So queue infos at 0. We can say vk device queue create info, but the thing is, one thing that's actually causing, like, has caused me trouble in the past, was that I just added both the queues to the queue create infos, but there is often the case that the graphics and present queue are both the same, right? So they're both the same queue, and then Vulkan just errors out. So queue family index will be the context graphics queue family, because the graphics queue family, we need to provide that. Flags will be, so I think we don't even need flags, but queue count, we need that, so this is 1. And then we need something like a priority, which is really really weird, bro. Really weird. Yeah. So yeah, priorities, and then we need to specify the priority. We just have a priority of 1.0 for all of the queues. Is equal to. Yeah, and then we just need the S type. So dot S type is equal to VK structure type device queue create info. Like that, and then we check if basically if graphics queue family index not equal context dot present queue family index, so it's two different queues. Then we want to add the present queue as well with the same thing. And then what we probably want is something like a n queues is equal to 0, and then do n queues plus plus and n queues plus plus, because we need to tell Vulkan how many queues we want in this info. So it's equal to queues, queue infos. I mean queue infos. Count is equal to, as I said, queue count, or that's not even queue counts, n queues, right? N queues, and yeah, and then we kind of need to also have enabled extensions, because what we want is a const sharp pointer device extensions, because one thing which is actually very insane to me, VK-KHR swap chain is an extension. So basically the ability to just swap pictures onto a surface, so basically to just, like, the core foundation of rendering in Vulkan is an extension. It's just like, it's like a plugin. You can theoretically like use it, but it's not like a core thing, right? No, it's not a core thing. Yeah. So this is the count, which will be 1, and key enabled extension names is device extensions, and yeah, that's it. Now we only need the S type, because yeah, it's very important and stuff like that. Device create info. Yeah, and then we can create the device already with the device info. Null for the allocator, and the device will be context. And now we need a logical def. So vk device logical def. So context dot logical def, and then we check if this is not equal to vk success. Okay, and then we return false and say fprintf std error failed to create Vulkan physical device. But let's not do that, because we don't do in the other logs as well. And we need to have Chad say that, because Chad is talking to you as you get the errors, right? That's basically the law. Okay. Yeah. Now the other thing is that we actually need a VK device queue, not just the index. It's a VK device. Wait, I don't know the name of the struct. VK get device queue. I think it's probably a VK queue, right? Yeah, VK queue. Okay, so we need a VK queue, graphics queue, and a present queue. Okay, gamers. And then we use the context.logical device with the context.graphics queue family index and wait, queue family index and queue index. I think queue index is 0. so this is context.graphicsQ and present Q filament index. This is the present Q. Right, so this is just creating the queues actually with a logical device, and they don't even return a result, so we can't even check if we got the queue, but whatever. Yeah, and this is it. So let's, if not create a logical device, we exit. And now we also need to log a successful message. By the way, we don't want to log that to std. Ah, we want actually. Never mind. So let's put here created logical device, like that. Okay, not making created logical device. Nice. First try, man. Okay, after the logical device, I'm pretty sure we get to the swap chain. Okay, so yeah, the next thing will be the swap chain, and the swap chain is a little bit more involved. So let's have a static bool create swap chain, takes in a chat context, a struct, or probably not struct. Let's have a chat swap chain basically, right? Swap chain, a uint32t width and height, because obviously we need some kind of width and height of our images. So let's have a type def struct chat swap chain. Yeah. So the swap chain will have some things. For example, we will have a vk image view pointer image views. Yeah, what else? Probably something like n image views, or at least like n images. We will have a one-to-one from images to image views. Image views is just a thing, just an abstraction over images, and images are basically the buffers. And the image views is to create the frame buffers that we will need to actually, yeah, basically present the pixels in Vulkan. That's why, yeah, we kind of need frame buffers as well, but frame buffers will be in another structure, which is a frame loop. Then we will need a vk extend dimensions, or dim. I think dim is cooler. A vk surface format, khr, which we will query, surf format. A vk present mode, khr, which we also will need to query, surf present mode. We will also need a vk format for the swap chain format that we want. And then of course we will need a vk swap chain khr, because swap chains are an extension, right? Let's call it swap chain handle. Okay. And create logical device. Where's create swap chain? Here. We will basically take in the swap chain, right? But it's a O swap chain. Okay, so we basically need another function that, let's call it get swap chain info. Because as I said, we need all of those things like the format and stuff like that. We also will need a context and basically a swap chain info. We will probably also need a swap chain info struct, so let's create that. It's basically going to contain all of those things. Chat swap chain info. So let's have that be a void, and then have a chat swap chain info O info. we will, by the way, we will also need N formats and a VK, I think it's surface capabilities, KHR, caps or surf caps. Because we will also need to create that. So let's have a VK get physical device properties. It's not properties, it's surface capabilities, KHR. With context dot physical device. Surface is going to be in the context dot surface. Surface capabilities will be. Wait, this is the wrong function, bro. I was like, what? Oinfos dot surf caps. Then we want to get the surface formats. Oh my god. Autocomplete, please. So surface formats, and this is surf FMTs. Ah, bruh, we obviously need a surf FMT. And we will probably don't need this because this is what the swap chain decides. We just need the surface formats, N formats, and present modes, like the available modes and the available and present modes basically. Yeah. Okay, so surface formats with surf. Yeah, now it works. Surf FMTs, but no, we it's a function like that. So yeah, we need to first say oinfo.nfmfts and then null at the end, and then we need to do oinfo.fmts, surf FMTs. And the same thing with the present modes. So get surface present modes KHR, surface present modes KHR, and present modes surf present modes. Thank you. Yeah, and then we don't return anything. Yeah, and then the thing for the VK, basically for the format that we want. Like basically getting the swap chain format. So basically, the swap chain has a surf format. We need to get that somehow. So let's return a VK surface format, get swap chain format, and it takes in a basically we just want to take in some formats. So let's have a VK surface format KHR FMTs and U infinity T NMFTs. And then we basically want to check if we have a format that we actually want, and the best format for us. So NFMFTs, I++. So basically, if FFTs at I.format is equal to VK format, format B8 R8, no, it's B8 G8 R8 sRGB. So that's our desired format. And FMTs at I.color space is equal to VK color space. Color space sRGB non-linear. So that's basically the most basic color space. Then we just want to return FMTs at I. And else we just return FMTs at 0. Because, like, can't really do anything about it, right? Might have to take that one. And And then also the same thing for the present modes. So VK present mode KHR gets swap chain present modes. N modes VK surface present modes N modes at I. Basically, we check if it's mailbox, because mailbox is the best present mode. So VK present mode mailbox, because it's like the most performant, least stuttering, least screen tearing. VK present mode. Oh, it's actually not surface present mode, right? It's like this. Okay, but that's kind of a problem because we get surface present modes. VK present mode. Okay, it also returns a VK present mode. So this is a VK present mode, and okay. Okay, so I think everything is good. Yeah, and then when we cannot do that, we just return FIFO, because that's the next best one. And then we just return modes at I. Yeah, and then also another thing is what we kind of need to do to be extra clear or extra like good, a good Vulkan user is get swap chain extend. And what we basically want is the capabilities. So VK swap chain capabilities. What's the name of that? Surface capabilities, actually. So because every Vulkan surface has a maximum extent, so maximum height and width. So let's get this like that. So, and then that's the capabilities, and then we want a width and height that the user provided, because like when we just provide something like 10 million by 10 million pixel surface, this will bail out and just say we don't have any place for that. So what we will do is say VK extend to the extent is equal to VK extends to the, and then dot width is equal to width and dot height is equal to height. And then what I will need is, let me just copy that in dev slash vortex envim source slash util.h. What? Envim source slash core slash util.h. VT min and VT max, yes. Where was my thing? Here. So we basically need those, because, yeah, that is important. So let's have max and min. Like this, and then we just say extend.width is equal to max capabilities dot max image extend dot width and extend dot width, right? And then extend dot height, but this is min, so it wouldn't make sense. So min, and this is min, and then height and height, and then max and min image extend and min image extend, and then we just return the extent. Okay. Okay, now finally for create swap chain, we need a, wait, what's the time left? 1 hour? No way. Bro, we are so cooked. Let's have an info, get swap chain info. What do I need? The context, okay. And okay, so we're getting the swap chain info, and we are getting the surface format KHR. FLT is get swap chain format with info dot surface formats and info dot nmfts, and vk present mode KHR. Mode is equal to get swap chain present mode. Not modes, man. Mode. Okay, so info dot self present modes, info dot n present modes. Okay, and then vk extend to the, please, man. Extend is equal to get swap chain extend. Why isn't it? What? Extend. Get swap chain extend with info dot surface capabilities, width and height. Yeah, and then what we will need is yeah, let's have something like n images is equal to info dot caps surface caps dot min images image count plus 1, so one more that we minimally need to have, and then we can check when info dot surface capabilities dot, that's min, bro, min dot max image count is greater than 0 and n images is greater than info dot surface capabilities dot max info image count, then we need to clamp it to info dot surface dot max image count. So that's how we check how many swap chain images we want. Then we need a VK swap chain create info. I think KHR, yes. KHR swap chain info. Dot S type is VK structure type swap chain create info. Oh, bro, I need to log in so much to actually get this challenge done. Context dot surface dot min image count is equal to n images dot image format is equal to format dot image extend is equal to extend dot image color space is equal to format dot color space. Present mode is equal to present mode dot pre-transform is equal to wait, info dot surface capabilities to current transform, yeah. Composite alpha vk composite alpha opaque bits, so no cool like pcom transparency for us. Image extend, image format, min image count, surface. We already specified the surface, okay. VK structure type, swap chain, create info KHR, okay. Clipped is equal to VK true. Dot, I think that's it, right? No, image array layers is also important. So one image array layer. Now this is it. So min image count, we already have this. Q family index. What? No, we don't need that. I think image usage is also important. So VK image usage color. Attachment. Composite alpha pre-transform present mode. Yeah, we already have all of that now. We don't need those. No. Okay. Okay, so I actually looked it up. So what we need is to actually check if we have a graphics queue family index which is not equal to qt.present queue family index, and then else. And when we don't have that, we just do create info. No, swap chain info. Swap chain info.image sharing mode is equal to vk sharing mode exclusive. So we want it to be only on the on one queue. And then if we have two queues, we need swap chain info dot image sharing mode is equal to vk sharing mode concurrent, so that they can correctly share all of the image data. Queue family count is equal to 2, and then we need to pass the families as indices. So families 2 is equal to swap chain info no context dot graphics queue family index context present queue family index, and then we say swap chain info dot pq family indices is equal to families. Okay, and then we can vk create swap chain khr context dot logical device with swap chain info. No. And then here all swap chain dot swap chain handle, and yeah, then we can do vk get swap chain images context dot logical device all swap chain dot swap chain handle like this, and n images will be on all swap chain dot n images. Swap chain images will be null at first, and then we want incompatible what? Ah, yeah, like this. Oh, swap chain. Wait. Okay. Shouldn't we use those? I'm not really sure. Let's just keep going because we don't have time. Swap chain. Oh, swap chain dot images. Yeah. Okay. But I think we need to first say all swap chain dot images is equal to Kellogg all swap chain dot n images size of vk image like that, and then we can already say all swap chain dot image views is equal to Kellogg all swap chain n images size of vk image view, and then we can assign all of these things like present mode is equal to mode all swap chain dot subs format is equal to format dot format all swap chain dot n images. Oh, we already have that. All swap chain dot dimension is important is equal to extends. Yeah, that's it. Okay, now we just have to create image views. So for unit 32i is equal to 0, I is less than all swap chain dot n images I plus plus, and then we say vk create image view with context dot logical device. What is that? Image view create info. Info is equal to that, and info null all swap chain and all swap chain dot image views at I. info s type vk structure type image view create info dot image is equal to o swap chain dot images at I dot format is equal to o swap chain dot service format view type vk image view type to d sub resource range. Oh no. Aspect mask vk aspect. Isn't it that? VK image aspect, yeah, color bit. Level count is 1 and layer count is 1. I think dot format. That's wrong. We need to say swap chain format. And this is swap chain format. And like the surface format. Surface format will be FMT. This is the swap chain format, and then we implicitly convert stuff. View type is equal to VK image view type. And then we do this, and then we say return true, and we say if that is not equal to VK success, we say return false, fprintf std error, chat failed to create Vulkan swap chain. Create that Vulkan swap chain. If that is not equal to VK success, do the same thing as here. Okay, I'm begging you to work. It would be very good if it worked first try. Let's have a chat swap chain in our context. Oh, context.swap chain. Let's have 640 by 480, as we have with the window. And VK success, create swap chain. Oh, bruh, like this. Segmentation fault, created logical device. Okay, where does it seg fault, man? Images, all swap chain images, and images. To where does it get? Does it get to here? Here. Okay. Maybe get swap chain info as a problem. No. Get swap chain format. Let's check that. Okay, problem lies here. Get swap chain format. NMFTs. MFT is as at I. Dot return MFTs at I at 0. NMFTs. MFTs. FMTs, I mean. Info.serve MFTs. Info.nmfts. Info. I mean, we never allocate them. So that's a problem. Oh, info dot serve MFTs is equal to curloc. Oh, info nmfts size of. Oh, info serve MFTs. Same with and serve present modes is equal to and present modes. Oh, that's a problem. Maybe this is also the problem. Let me quickly comment that out to check if that was the problem. So n present modes, serve present modes, NFTs, serve MFTs. Okay. Okay, so this was not the problem. Serve present mods. Created Vulkan swap chain. Nice. Okay, perfect. No frame loop. Oh my god, this will take so long. We will never get the time right. Static bool. Create frame loop. We will need a chat context CTX. And a frame loop. Yeah. So let's create a frame loop struct. So type the struct chat frame loop. We will need, as I said, the frame buffers. So let's have a VK frame buffer, FMTs, UN32T NFFTs. We will need a render pass, which is bound to that. So render pass, struct yeah, and we will also need our frames in here. What's your problem here? So basically we need a chat frame as well. So a chat frame, and we will have a chat frame frames. And we will have a, because this is basically our ring buffer of frames. This is like the entire reason we have a separate struct for this frame loop, because we want a frame index and have a ring buffer for that. So like this. And then we need a, then we need per frame, we need fences and semaphores. Because the frames will need the image available semaphore, which we will get from the extension acquire image for the swap chain. Then we need a render finished per frame, or let's just call it image render finished, because like this function will be finished, will be per frame basically. To correctly do that, Vulkan just requires you to have it like that. And then we need a VK fence, in-flight fence, right? And this fence is basically signaled by the graphics queue, or the present queue, I don't know. I think the graphics queue, and it just tells us who is currently using that frame, and basically making it so that no concurrency issues are happening. Yeah, and then we need a VK command pool, and a VK command buffer per frame. You will see later. I am figuring we should already have a struct chat batching state, because we will need that for our 1 million things, right? Okay, so chat batching state. It will basically have a okay, so for the chat batching state, what we need is a chat GPU buffer. That's the last one, I promise. And it will have a VK buffer, and I think it's size T, a buffer size, a void pointer of the memory handle, because we will just use host coherent mapped memory. Then we will need a yeah, we kind of will need VMA, Vulkan memory allocator. So what's the time? 44. So VMA, let's get VMA, please. VMA GitHub. Source Oh god. Include? Yeah, thank you. Download raw file. Move downloads. Move downloads dash vk memalloc.h dot. Okay. And what we basically want is to say hash include vk memalloc and then hash define vk vma implementation. Yeah. Like this. I don't know what's your problem here. So I think what we definitely will need is, let's try and compile that actually. So GCC like that. Yeah, we will need -l std c++. But that's actually bad. Can't we like use that and see? That's. Let me check that. We will need to compile with G++. I'm very sorry. That's the easiest thing, easiest fix. No, bro, please. Okay. Let's just say vma.cpp and link them both together. And just have this thing be in the CPP file and have this thing be here and just separately say gp plus dash o dash c, I guess, vma.cpp vma dash o vma.o. Yeah, and then we need gcc dash c chat.c dash o chat.o and then dash l vulkan dash l gfw. Okay. Create frame loop. Yeah, we need a chat frame loop. Turn true. Now my question is, how do I link? Is it like AR link to .o files into a .exe into a executable file? Can I just say gcc vma.o chat.o dash o chat undefined reference, okay, dash l gfw dash l vulkan dash l std c++. Okay, thank you. Nice. Okay, now we integrated that. Okay, so now for utility I is equal to 0, I is less than cr max frames, I plus plus, and then like chat frame is equal to loop frames at I, vk create command pool basically, right? So vk create command pool because we need to create the command pools. So loop, no, it's frame. This is context logical dev. Create info. Vk command pool. Create info. Pool info is equal to .s type is equal to vk. I think this is a pretty easy structure. Structure type command pool create info. Flags is going to be vk command pool create reset command buffer bit. And then we need the Q family index, which will be context.graphics Q family index. So pool info null and frame dot command buffer. Okay. What's command pool? Initializing frame with expression. Oh. Okay, so now we need to have the command buffer allocate info, buff info, create the command buffer, command pool. It takes in the command pool, which is frame command pool. Then it takes in command buffer count, which will be 1, level, which will be vk command buffer level primary. No, not secondary. Primary, and S type is vk structure type commands buffer allocate info, and we create the vk allocate command buffers. Logical device, and what is that? Is the buff info. And the command buffers we want to allocate is frame.command buffer. Okay, now for the semaphores, vk creates semaphores. Or semaphore? Yes. Context or logical device. Okay, then for the semaphore info, sem-info, we just need the S type here because, yeah. vk structure type semaphore create info. So the semaphore info, null for the allocator. Semaphore is going to be context dot frame dot image available. Need to close because of the autocomplete. Frame dot image available. And now for the render image per frame, we actually need to frame dot. Where is render finished? Didn't we create that? Finished. Render finished, man. Render finished. We need to catalog as many semaphores as we have context.swapchain.images, because later we will get the index to this, which has a bounds of n images, the index. Okay, this is just size of frame render finished. And then we say for u and 32 I is equal to 0, I is less than context.swapchain.animages, I++. We just create the semaphore like this. Render finished at I. And then we just need to create the fence, so vk create fence with context logical device const vk fence create info, fence info to S type, vk structure type, fence create info. And then we need flags as vk fence create signodes. Create signodes, and then we pass the info. Null. And the fence is the frame dot in flight fence, right? To correctly fence everything off. And this is it for this. Okay, so I just copied the render pass info from another project, because typing all of this out would take so much time. Context dot, that's actually already great. So surf dot swap chain format, right? Okay, and then after that we can just vk create render pass, right? So let's have physical device context dot logical device, I mean, and this is the pass info, null, and basically the render pass is just it basically makes it, for example, that you can clear the screen, and we only need to allocate the render pass once. So loop dot render pass, basically the thing that we need to bind when rendering. Yeah. Okay, now creating the frame buffers. I need to look how that works. So let's try that. Create frame buffer with context.logical device. Create info will be yeah. VK frame buffer create info. Info is equal to S type, VK structure type, frame buffer create info, and okay, we need a render pass. We just created a render pass, so loop render pass. Then an attachment count. I think we want one attachment. But I think, yeah, the p attachments is. So we basically need to iterate the image views for that. Bro, no, thank you. Yeah, so we basically need a VK image view attachments is equal to context.swapchain.image views at I, and then we need to allocate them. I mean, iterate them. So I is less than context.swapchain.n images I++, create the frame buffer, do this, and by the way, we also need, I think we need, yeah, width and height. Cause like this makes sense, right? So context.swapchain dot dim dot width, and height is context dim dot height. Like that. Please, please, please. What? P attachment is equal to attachment, sorry. And render pass will be without that. And now we only need layers, which is one layer of frame buffer, right? And okay, so now we pass the info, pass the allocator, pass the frame buffer, loop.fps, loop. Oh, did we not? VK frame buffer, MFTs. I'm sorry for that. Loop.fps at I. Create the frame buffer like that, right? And I think that's it for the frame loop, right? Let's try creating the frame loop now. Create frame loop. So we will need a chat frame loop. Context of frame loop. Let's just print fprintf stdout chat created frame loop. Oh, how many minutes? 29 minutes left. Oh my god. Created Vulkan swap chain. Please, why didn't because what? Why didn't it? We need to compile a weird thing. We definitely need some bash.sh, and let's have dev/chat Vulkan chat. So this, we want that basically. And then we want gc. No, we want to say -c that basically. and then this. And then let's just dot slash chat. Mode plus x. Fuck. Fuck. So let's see, maybe here. Here. Created Vulkan structure. Not even here. CR max frames. Create command pool with the pool info Q family index. Null. What is null here? No, allocator. Command pool. Context or logical def. So basically this failed. You're telling me this failed. Dot slash dash. I have a feeling. Here. So this always works. Okay, so this always works. Create render pass. Here. Attachments. Swap chain image views. Ah, maybe we didn't like allocate image views? We did. Size of VK image view. Okay. Ah, FBs. We definitely need to allocate FBs. Loop FBs equal to calloc. Context.swapchain.nimages. Size of loop FBs. Okay. Nice, created frame loop. Now let's draw a frame. Let's have something like, actually what we will want is something like static void draw begin and draw end, because we want a nice batching system. So chat context, and then what we basically want is, yeah, we will want, not struct, we want to get the chat frame is equal to context.frameloop.frames at context.frameloop.frame index, right? And by the way, let's say we want to memset 0 size of context. This is pretty important. Initializing chat frame wrong. Oh my goodness. Okay. And then we basically want to VK wait for the fence of the frame. Context dot logical device for one frame for one fence, and then frame in flight fence. Wait all this VK true. UN64T max for the delay or something, or like timeout. Yeah. Okay, and then we want to VK acquire next image KHR, and this takes in the logical device, context.swapchain.swapchain handle, and timeout UN64T this, and then it takes in the image available semaphore, so frame image available, and fence is the VK null handle, because we don't really need a fence for that, and the image index, yeah, that's pretty important. it's a swap chain image index, and we need to have that for the render finish semaphores. So swap chain image index, because we need that in the other render end function. So context.swap chain image index, store that, and yeah. So then we want to reset fences, context.logical, basically at the beginning of the frame, we reset all of the fences and semaphores. Not the semaphores though. Context, no, it's frame.inFlight fence, right? We want to reset that. Then we reset the command pool, so we don't accumulate commands. Context.logical device, frame.command pool, no flags. And then, yeah, then we have a command buffer, begin info. Begin info is equal to vk, yeah, just that, vk structure type, command buffer, begin info. And then we want to vk begin command buffer with frame, and that's basically our buffer where we store draw commands in. So begin info, and then we can already have a vk command begin render pass, and in the render pass we can do stuff like specify the clear color, which would be great. So p render pass begin is a vk render pass begin info, render pass info, vk2.s type is vk structure type, render pass begin info dot render pass is equal to context dot frame loop dot render pass, and frame buffer is equal to context dot frame loop dot frame buffers at context dot swapchain image index, and then render area will be dot offset is equal to 0, dot extend is equal to context dot swapchain dimensions. Mamo, ja nie mogę teraz. Nie mogę.
Ja, aber wo bist du?
Zu Hause, ich mache ein Video.
Okay, aber nachher.
Okay, ja, okay, ciao, ciao. So the done. And p clear values, right? That's the cool thing. P clear values is equal to, and then we have a vk clear value. Clear is equal to, and then we can have right. Dot color is equal to, and what does it take in? I think we can just say something like 0.1, 0.1, 0.1, 1.0, and then say p clear value is equal to clear, and clear value count is 1, and then we can begin the render pass with the render pass info, and contents. What is content? Subpass contents, vk subpass contents inline. Yes. Like that. Okay, and then we have the begin, right? Okay, now the draw ends. Void draw ends. Takes in a chat context, ctx, and here we basically want to, in the end, like when we implemented that, we want to render here. But now we just want to command end render pass for now. With frame, no, we need to get frame. So with the frame command buff, and then we want, no, with the frame, yes, it takes in the command buffer, yes. vk command end command buffer. End command buffer, yes. And yeah, and then we want to submit to the graphics queue basically what we just did. And for that, we get the submit info, and it takes in stuff like S-type, VK structure type, submit info, and yeah, wait semaphore count is going to be 1. P wait semaphores is and frame dot image available. Signal semaphore is okay. So this is basically frame dot render finished at context dot finished at context dot frame loop dot, no, it's just context, right? Yeah, we'll store that in context. And then signal semaphores count will be 1. And then we need p wait destination stage mask will be pipeline flags. So we will have a VK pipeline. What is that? Hello? Oh my god. A const VK pipeline stage flags. VK pipeline stage flags. Hello? Flags. Why? VK pipeline stage flags. Yeah, flags. Is equal to VK pipeline state, yeah, this, right? We want to stage to that, and that's that's basically our pipeline state, I think, or stage. So flags. Command buffer count will be 1, and p command buffers will be frame dot command buffer. I think that's it. Yeah, and then we just vkq submit to the graphics queue. vkq submit to context.graphics queue. One submission of the submit info. Fence will be frame and flight fence, right? Because that's basically the usage of the fence. It's going to tell us when the graphics queue is not used anymore and we don't use any graphics resources. And then we say we need a vk present info as well. So vk present info is equal to info is equal to .s type, vk structure type, present info hr. Wait semaphore count is 1, p wait semaphores is basically that, and p wait semaphores, and then the swap chain count is 1, p swap chains is and context.swap chain dot swap chain handle, and p image indices will be just our swap chain image index. So with that information, and also it's going to basically wait till the graphics queue is finished, right? Because we specify the same semaphore. Present KHR, we basically want to present on our present queue. And with the present info. And then the very important part, I shouldn't forget that, context.frameloop.frameindex is equal to context.frameloop.frameindex plus 1% CR max frames, right? And then we, do we return anything? No. Okay, let's try that. Draw begin, context, draw end. Context. Let's fucking go. Do you see that, man? Oh my god, man. How many minutes are really left? 13. Oh my god, it's such a sad thing. Okay, what we need to do next to actually see stuff on the screen is compile shaders. So let's create our instanced vertex instanced vert.glsl. Hash version 450 layout location is equal to 0. In vec2 apos, basically, or like a vertpos, I guess. And then what we're going to do is location 1, 2, 3 will be the actual instance position, instance size, and instance color. And location is equal to 0. Out vec4 v color, right? And then we will have a push constant. So push constant uniform. Push constant is basically like a uniform, right? Constant push constant. And we will need a NDC to pixel scale and NDC to pixel offset, right? Because our goal is to have something like those vertex positions, and we just need to multiply them by the formula. So GL position is equal to a vertpos times the instance size plus the instance position. And then what we're going to do is say, because we need to, because you know those are all in pixel space, but to convert them we can just say times wait, we need to specify the name of the push constant. So pc dot ndc to pixel scale plus pc dot ndc to pixels offset, and then 0 and 1. And this is basically the formula. Like, that's not really the formula, but this will be the formula, and offset will just be 1, and this will just be like yeah, like the formula. I think it's 2 divided by width, screen width or something. I really don't know. I need to look that up later. Color pro v color is equal to I color. That's important to get in the vertex in the fragment shader, and then the instanced frag.glsl will just be hash version 450 layout location is equal to 0 in vec4 v color, and then location out o color void main o color is equal to v color, like that. And then we need to create our pipeline. So after create swap chain, let's just put that into create swap chain. Oh no, I think it's not really, doesn't really make sense. I thought like because of time and shit, but yeah. Create pipeline with, I'm always thinking struct because I never typed with my structs, but whatever. Yeah, and then we just create shader module, right? So I think it's vk create shader module. Yeah, so basically this, and vk create shader module takes in the context of logical device, and a vk shader module create info is equal to .s type is vk structure type hello, why, what, vk structure type shader module create info code size, right? And what else? And like the code, right? So what we will need is to read a file. I am just going to copy the read file function. Let's just call it util read file. So we are basically going to say unsigned char pointer code is equal to read file size t code size, and it takes in instanced vert.glsl and code size. This is like info, and this is code size, and p code will be code. Incompatible pointer. What? Ah, okay. It's a UN32T. Okay, so and then let's say info, no shader module. Let's have a VK shader module, vert, and then basically do the same for the fragment shader. And let's just have them like this. Frag. And this just takes in the vert, and this takes in the frag, and this takes in frag. Yeah, and then we need a VK pipeline. Bro, is the time up? No, 6 minutes. Oh, we do not get the time. Shader stage, create info, shader stages. We will have 2 stages. And VK pipeline shader stage, create info. S type is VK structure type shader stage create info. Stage is VK shader stage vertex, because this is basically the vertex shader stage. P name will need the main function, the name of the main function, we call it main. Module, it's just a shader module, so let's say vert. And let's do the same thing for frag and say fragment. Right. Okay, so I copied all of the like very unnecessary pipeline stuff. For example, blend mode, rasterizer, how our polygons are going to be rasterized and stuff like that. Because it's like very basic and it's like a lot of typing. It's just like from the Vulkan example, so you can just easily look that up. Blend state. Yeah, and then what we will need is actually a pipeline layout, which includes the push constants. So the pipeline layout is just like baked into the pipeline, and with that, push constants are baked into the pipeline. So push constant range and push constants are, as I just said earlier, just uniforms, and they're per pipeline. Offset is 0, stage flags is VK shade stage vertex shader, because we use it in the vertex shader. Size is equal to size of, and then we will need the push constant in here. So chat push constant. And just has a vec2 offset and a vec2 scale, as we just had it. Oh, we need to include CGLM as well. CGLM/cgml.h. Okay, so size of chat push constant. Did you mean what? Oh, type def. Okay, so basically this, and then we need a VK pipeline. Basically, how is it called? VK pipeline layout create info. Yes. Layouts is equal to S type, V structure type, pipeline. Layout create info. Push constant range is equal to range, and push constant range count is 1. Create pipeline layouts is context logical device, layout info, no, and the pipeline layout is going to be, yeah, we need to store that. So vk pipeline layouts, pipeline layouts. And while we're here, let's have a vk pipeline because we will also need the pipeline. So range and pipeline layouts. Context pipeline layouts. What? Where did I just put that in? Bruh, in the swap chain. Okay. Okay, so pipeline layout, and yeah, and then okay, I just copied the dynamic states as well. It's just the viewport and scissor state, because we're going to set them dynamically. Okay, now it's going to be the vertex layout, basically similar to OpenGL, you know, the vertex layout thing. So for that, we will have a struct. Wait, we did that wrong. Type def struct. Type def struct chat batching state and type def struct. Okay, so we need a type def struct chat vertex, which just has a position. We need a Chad instance, and this has a position, a size, and a vec for color, right? And because we will need that for the offsets in our pipeline. So pipeline, create pipeline. Where is it? Here. Okay, so basically we need 2 binding descriptions, because for one we have this binding and we have this binding, and the one is an instance binding and the other one is a normal vertex binding, so they're not the same. So basically binding descriptions, we have 2 of them, is equal to, first one is going to be, hello? Binding is equal to 0. Why do I don't get autocomplete? Maybe vk vertex inputs binding description. Yeah, stride is equal to size of chat vertex, because that's just the vertex. And input rate is going to be vk vertex input rate vertex. So it's a normal vertex layout thing. The next binding will be the chat instance, and it will be instance rate. This will be binding 1. Oh my god, the time is up. No matter, it doesn't, I don't care. Attribute description, vert attributes, right? So basically the attributes. So we're going to have vk vertex input attribute description, location is going to be 0. But that's for the first one now. So binding is 0 because it's of the vertex. Offset is yeah, it's like we can say something like offset of chat vertex and pos, right? But it's just 0, so it doesn't really matter, but still. Then the format is going to be VK format R32 G32 S float, because that's basically how you specify vec2 in Vulkan input layouts. So that's that. Then we will have one more. So location is going to be 1, binding is also 1, and this will be offset of chat instance pos, but this will be the same. This will be chat instance size and location 2, 1 for here, and this will be still the same. And here we need G32, RG, B32, and A32. Okay. Location is 3, and this will be color. Okay. Okay, then we need to create the vertex input state. So VK pipeline vertex input state create info. Vertex input state is equal to VK pipeline vertex input state create info. S type is VK structure type pipeline vertex input state create info dot vertex binding description count is 2, as we said, and dot vertex binding descriptions is just binding desk, and dot attributes description count is 4, and attribute descriptions is vert attrs. That's it. And now we can create the pipeline. So VK, we always need more info, so now we need an info for the pipeline again. Which is going to be have S type VK structure type graphics pipeline create info. Stage count is going to be 2, and P stages is going to be shader stages. And vertex input state is going to be vertex input state. Then we have all of the other states like input assembly state, input assembly state. I just copied them because they're just like very benign. I think it's assembly state. Assembly state? Yeah. Color blend states is going to be blend states, and then we also have a multi-sample states, MSR states. Right, and then we have a rasterization state is equal to raster state, P dynamic state, also that is going to be dynamic state, and then the viewport state is going to be the viewport state, and then we just need the layout, which is the context.pipeline layout, and render pass is going to be context.frameloop.render pass, and then we need subpass 0 because we said subpass is 0 in our render pass, right? Then we can, by the way, we need to destroy the shader modules, right? Because after creating the pipeline, they are baked into that. But let's first create the pipeline. VK create graphics pipelines, context.logical device, pipeline cache is VK null handle, one pipeline, pipeline info, null allocator, and pipelines is going to be context.pipeline. Yeah, and then we can destroy them all, but I don't really care. Let's just say something like return true, and something like fprintf stdout chat created graphics pipeline. Okay, I'm just going to assume this will work. I think the more important thing will be our GPU buffer functions. So let's create them. Basically, static bool create GPU buffer, and it will take in a chat context, CTX, a VK device size for the size of the buffer, a VK buffer usage flags for the usage, basically things that we need to pass to VMA because we let them do all of the heavy lifting, memory properties, and then a chat buffer OBuff, right? And then what we want is to do VMA create buffer, and we need a VMA allocator. So let's have a VMA allocator, VMA. Let's have VMA, context of VMA, I mean. Then the buffer create info is going to be a buffer info. So VK buffer create info, buffer info is equal to .s type is VK structure type buffer create info. Size is equal to size, usage is usage, and then we need a what is it? Yeah, allocation create info. Alloc info is equal to usage is VMA memory usage auto dot required flags is memprops, and then flags is going to be VMA allocation create mapped, because as I said, we want host coherent memory, and then we want VMA allocation create host access random. I looked that up myself, and it's basically request possibility to map the allocation, right? So we need to specify that. If I don't, then Vulkan validation layer just tells me that, so I just did that. Okay, so alloc info dot no, that's actually it, right? Yeah. So let's just have our buffer info in here, our alloc info, and our buffer is going to be yeah, we need a VK buffer basically. So VK buffer buff, so buff allocation. I think we also need a VMA allocation. Alloc, alloc, and allocation info is going to be alloc info. Yeah, and then to actually get them, so this basically created the buffer, right? Need to do that like this. And then to actually get the memory handle to the buffer, we need to do VMA get allocation info, and it basically returns us a VMA allocation info, and we can pass it basically our buffer. So I think context.vma and allocation is going to be alloc. And we just pass the info, and then we just can say something like mem handle, yes, and we also need a VMA allocation, VMA alloc. But I don't know, do we even need to store that? Yeah, probably before the resizing, yeah. We will need the usage flags also for the resizing. So VK buffer usage flags, usage, and VK memory property flags, memprops, right? Okay, so let's use alloc. Wait, incompatible pointer type, VK, VMA allocation create info. VMA allocation info. Okay. Ah, wait. So buffer info, alloc info. I think this is just null, right? And Yeah, we don't need that. Okay, so basically we say obuff.memHandle is equal to info.pmapData, right? And obuff.buff is equal to buff. obuff.vma_alloc is equal to alloc. obuff.buffSize is equal to size, so size. obuff.memprops is equal to memprops. obuff.usage is equal to usage. And then we just return true. Let's just always return true, I don't care anymore. Okay, then a function to destroy a GPU buffer. It's going to be important because we will want to resize our buffers, and for resizing our buffers we need to destroy them. So destroy GPU buffer, cr context. So we need a chat context ctx and a chat GPU buffer buff. And this will just do vk device wait idle. Yeah, that's important because we cannot destroy resources when the device isn't finished with them. So vma destroy buffer context.vma buffer.buff. Yeah, and then here we need the allocation for buff.vma_alloc. And then we can say something like memset buff 0 size of buff. And we just return true. Now the big one, oh, it's not even big, but still the important one, resize GPU buffer. It's going to take not an struct, but a chat context ctx, a chat GPU buffer buff, and a new size. VK device size, new size. And we are basically going to create a new buffer. So not struct, but chat GPU buffer new buff. And we say create GPU buffer context new size and then buff.usage and buff.memprops, and new buff is the new buffer. And context is just normally context. And then what we want is just to mem copy the old contents to the new buffer. So we're just going to say, yeah, let's just say mem copy like this. Mem copy the new buff dot mem handle into buff dot mem handle, and basically copy. So what we basically want to do is copy the into the new buff the old data, so that we retain the old data, and n is going to be the min between, I mean, we can just say new size, but because we are never going to downsize, but we can say the min between this and the original buffer size. So buff.size. And then we just destroy the old buffer. So we destroy this buffer, and we just say buff is equal to new buff. Right? And then we just return true. And that's basically that. Okay, now we actually want to say create batch state. And it takes in a chat context, and a, yeah, we definitely need the batch state per frame, because all of the batch data needs to be per frame. So let's have a chat batching state, batching, because in we already have this like rotating frame system, and it's going to be perfect for correctly maintaining data and not getting any access violations. So that's basically the right move. What we're going to need is a chat GPU buffer, VBO, and a instance buffer. Yeah, and then we're probably also going to need an IBO. Then we're going to need something like n instances. And an instance write offset. Basically the offset into which we want to write in the memory of our instance buffer. A uinfinity batch group cap, right? Yeah, okay, and then let's have something like hash define max instances. Let's have 10,000 per batch, or instances per batch, 10,000, and hash define initial batch cap. So how many batches we have initially? Let's have 8 batches. So that we don't have to resize so often. And create batch state. Yes, it's going to take in a chat frame, as I said. Frame. And yeah, we are basically going to create the GPU buffer. So create GPU buffer. Context size is going to be 4 times size of chat vertex, because this is going to be our VBO, which just going to store the vertices for our instance. Usage is going to be VK buffer usage vertex buffer. Memory properties is going to be VK memory property host visible and host coherent. Host. It's just the easiest way to map memory, right? It's not the most efficient, but still. Frame dot batching dot VBO. It's going to be the buffer. Passing it like that. Return true in here. And yeah, and then we can just do something like let's just copy that for data. Struct chat vertex vertices is equal to frame.batching.vbo.memhandle. And yeah, and this should work. And then we just say vertices at 0 is equal to chat vertex.pos is equal to, and then the first one will be 0, 0, as you know. So 0, 0. Incomplete type chat vertex. What? Chat vertex is not incomplete, man. Ah, sorry, like this. So chat vertex, and then we have 1, 1, 1, 0, 1, 1, and then 0, 1. Okay, so after creating those, the next thing will be to create the GPU buffer for the indices. So basically that, and then we say IBO. But this is also going to be static. The only thing that's going to be dynamic is the instance buffer, right? So let's have it's like instances per batch times initial batch cap times size of chat instance. So that's basically the number of instances we can store in the buffer initially. This is also going to be a vertex buffer, but this is an index buffer. Yeah, and then this is going to be batching.instance buffer. And the memory usage is still the same. And yeah, and then we just need to assign the indices. So indices is equal to yeah, we don't really need to cast that, but we can say frame.batching.IBO .memHandle. That's the indices, and then we just have the basic quad indices. So indices at 0 is 0, and then like 1, 2, and then 2, 3, 0. So 2, 3, 0, and this is like 5, 4, 3, 2, 1. And yeah, that's already it for the setup of the batch state. So we want to do that per frame in the frame loop, the setup. So basically after that, we basically want to say frame that batching is equal to chat batching state 0, and then we just say create batch state context frame, and yeah, that's basically that. And but then we definitely need to after the swap chain create the pipeline, and also create the VMA. I think we need to do this like that, but we definitely want to create the VMA before the frame loop, because we are doing VMA stuff inside the frame loop. So let's have a rule create VMA chat context ctx return true, and this is just going to do VMA create allocator create info is going to be VMA allocator create info, VMA allocator create info, alloc info is going to be takes in device, which is context of logical device, takes in the physical device, which is context of physical device, and it takes in the instance, which is context of instance. Basically all of the name a better trio. Pro, it just takes in all of them. And then we have alloc info, and the allocator is going to be context.vma. So context.vma. And then before the pipeline, we do create VMA exit 1. Yeah, that's basically that. Okay, and then in draw begin, we are going to need to do something. For example, we definitely need to say frame.batching.instance instance write offset is equal to 0, right? Because we want to reset that every frame. Then batching dot n instances is also equal to 0. And yeah, that's basically that. What we're also going to have is a let me see. Yeah, no, we definitely need a function called something like render flush, and render flush is going to do something very interesting. And first also we need something like static void render begin batch. Let's actually draw, right? But I think no, let's have them like this, because the draw functions are like the public things. And so let's have a chat frame, takes in a chat context, And we have frame.batching.n instance is equal to 0 when we want to begin a new batch. Flushing, we are just going to take the frame again and say something like frame.batching.instance write offset plus equals to the basically, yeah, the frame.batching n instances in the currently like flushed batch. So we don't overwrite the data before the GPU actually, because like we are going to flush it by saying command draw very soon, but this is actually just going to record it and not draw it instantly. And that's why we need a write offset, and we cannot just say instant write offset is equal to 0 again, because we are not sure if it even drew at this point. So we definitely need to do that basically. And yeah, so then we need to draw call. And for that, this is going to be happening. And by the way, we need to say frame.batching n is equal to 0 after that as well. Yeah, this is going to happen here. And what we're going to want to do is vk bind vertex buffers, right? So with the frame command buffer, first binding is 0, bind count is 2, and then p buffers is going to be vk buffer buffs is equal to that, and then like frame dot batching dot vbo dot buff, and then instance buffer dot buff, and then we have the buffs, and then we also need offsets. Yeah, basically the offset is going to be the offset that we have, so vbo offsets. So 0 for the static one, and then we have then we basically have frame.batching.instance write offset times size of instance. So that's going to be the offset, so that the GPU also knows about them. VBO offsets. Oh yeah, sorry. Just like this. And then we just need to bind our index buffer, so command bind index buffer, frame command buffer, index buffer is going to be frame.batching.ibo, offset is 0, and this is vk index type uint32t. Oh, uint32. 32, yeah. We need the buffer actually. And yeah, and then we can just vk draw indexed. Vk command draw indexed with frame dot command buffer 6, and instances is command dot in instances is just going to be frame dot batching and instances. First in the index is 0, first instance on all 0, right? What's your problem? Buff. Didn't I already do that? This is basically the flush function. Now we just need a function to actually draw a rect. So static void draw rect. Chat context, ctx, float x, float y, float width, float height. By the way, one thing that I missed. Yeah, but we're going to do that later. Okay, so let's have the frame. And then we just want to check if frame.batching.instances is greater than or equal to what is it called, like instances per batch Then we want to flush. Context. And yeah, and then we say and by the way, let's go to here and say render begin batch. Context. Let's put that up here. Okay, and then we want the index basically, so the index in which we are going to insert the instance. It's going to be very, very simple, just frame.batching. Instance write offset plus frame.batching and instances, right? And then we need to check if that index is exceeding. Yeah, basically. Okay, so we basically want something like a total capacity. Total instance capacity. If that is exceeding frame.batching total instance capacity. What's your problem? Okay. So total instance capacity. Then we want to say, and before I forget, let's just say in create frame loop, create batch state, basically say frame.batching.total instance cap is equal to that, and then frame.batching total instance capacity, total instance capacity. Then we say frame.batching.total instance capacity is times equal to, yeah, good growth factor, I guess. And then we check resize, and then we check resize buffer. We do resize buffer. Context frame.batching.instance buffer. We want to resize that to basically frame.batching.total instance capacity times size of chat instance. So basically resize to the new size. Frame.batching.total instance capacity times size of chat instance. And yeah, that's basically that, right? What's your oh my god, what the fuck happened? Okay. So we resize that buffer, and then we just do struct chat instances is equal to frame.batching instance buffer.memhandle, and then we do instances at the index is equal to chat instance dot pos is equal to, and then we need something like xy, size is equal to width height, and then we need float r, float g, float b, float a, and then we say dot color is equal to r, g, b, a. Okay. And this is going to be at the index, and I'm just going to say frame.batching n instances plus, right? Oh, right, it's index like this. And instances, oh, it's also not a struct, nice. Okay, now in draw end, we need to actually draw, right? So what we basically want to do is before we submit and do stuff like that and end the rendering, we actually want to set the dynamic state first. So viewport and scissoring and stuff like this. Scissoring, bro. Yeah, the scissor, we want to set that. Okay, and then width is equal to context.swapchain dot dimensions dot width. Height is going to be height dot min depth is equal to 0 and max depth is equal to 1, right? And then we say vk command set viewport. frame command buffer 0, 1 viewport. That's it. And then vk rect to d for the scissor is equal to dot offset is 0, 0 dot extend the swap chain context dot swap chain. Oh, please. Dimensions, and then we set the scissor with vk command set scissor. And it takes in the command buffer 0, 1 scissor. Yeah, and then important thing, we need to submit our push constants. So it's actually not struct, it's just push constant, chat push constant. PC is equal to dot scale is equal to, as I said, the 2 divided by width and 2 divided by height, basically. So 2 divided by what is am I retarded? Context dot probably I had really a brain lag. With and this is context dot swap chain dot dim dot height divided, yeah, like this. And scale offset is going to be, because like this would return -1 to 1, but we need to offset this by -1, -1. It would actually return 0 to 2, by the way, and this then returns -1 to 1. Right, because we take -1 from each side. Okay, nice. Yeah, then we end the command buffer, but yeah, before we do that, we want to actually say if frame.batching.n instances is greater than 0, we have something to render. We want to bind the pipeline frame.commandbuff, and this is going to be vk pipeline, I think, bind point graphics. It's going to be the pipeline. So we are going to bind our pipeline, and yeah, and then we're going to that's actually dumb because we need to do that before, and then we can do that even only when we have something. And yeah, and then we can just flush. So basically render flush with the context, and yeah, that's basically that. I think that might be it. Might be it, actually. Am I forgetting something? Okay, I don't know. It will probably not run, but I think that's everything. So let's do bash.sh. Fail to open file, no such file or directory. Okay. So instanced verts.gsl. Instanced. Yeah, that's a problem. Instanced. Okay, now you have a validation error. Code size must be multiple of 4. You might have to multiply by size of u32t. Okay. I'm actually pretty dumb, because we actually need to glslc the shader first. So glslc instanced vert, so basically this. Yeah, and then we need to say dash f shader stage is equal to fragment. Yeah, and then we get a spare v file. So let's have vertex. This is instanced vert. Arrow assign cannot assign. What? This is 17. Eye color. V color is equal to. Oh. Okay, so like this. Then we have instant a dot spur v, bruh. So dash o vert dot spur v. This is going to be dash o frag dot spur v. So where's vert dot spur v and frag dot spur v? Okay, and then we can say frag dot spur v and vert dot spur v. And yeah, and this should work, right? It will probably not. No such file directory. Vert.spur v frag.bar. Spur v. Okay. Yeah. I feel like we don't really see anything, but it might be only a feeling. Oh, bro, I mean, we're not even drawing erect. Bro. Okay, yeah, that's kind of insane. 50-50, 100, 100. Let's have 1, 0, 0, 1. Okay. So now we get all of the problems. Draw index, use push constant, but VK push was not yet called for pipeline layout. What? Are you telling me I'm not setting the push constant? We bind the pipeline and we kind of... we never set the push constant. I'm dumb. VK, but it's actually push constants. It's actually very good debug, right? The validation layers and stuff. So the layout is going to be context.pipeline layout. Stage flags is going to be VK vertex. Where's like the stage? VK shader stage vertex bit. Offset of 0. Size of the chat push constant. PC. Okay, guys. Okay, gamers. Let's see if that did something. No. But at least we don't get an error, I guess. Okay, gamers. So basically, what I had wrong is that, yeah, I had this like this. So basically vertices were completely off. And the next thing was that I had this like that, but in the push constant we specified the other way around. And this is, I just changed that. Look at that. Okay. Right? Right. Okay, so let's try drawing 2 of them. 100, 100, that. Yo, yo, yo! Look at that! Okay, now textures, guys. Okay, my recording just crashed and there's another 2 hours, but I think we're not going to need them, I hope. But let's just try and make 1,000 of these. So something like sran times 0, and then basically need to check something, how I generate a random float. Okay, so basically R is equal to float rand divided by float rand max divided by 1. This is the same for G and B. And yeah, and then we kind of also need something like X is equal to rand percent context dot swap chain dot dimensions dot width, Y is dimensions dot height, and then we draw at X, Y, let's say 2020, and R, G, and B. So R, G, B. Yeah, we're not going to randomize alpha because it is be a mess. Going to not core render but Vulkan chat. So let's bash that. Yeah, so we have some problems with time.h. Drawrec, too few functions. Drawrec 2020. Why do I not get any? Bruh. Okay, nice. What we should probably do is go into bash.sh and compile everything. I don't know if we need to do it for probably like, let's just say dash O3. Let's just try the dash. Does it now compile with O3? I don't even know. Maybe we need to put that in here. Probably right. Okay, so dash O3 dash F fast math dash F fast math fast dash F unroll loops for maximum performance. I mean, it's not looking like it's struggling. I mean, we can't resize, but yeah. Okay, so we're drawing those rects there. What if we draw, what if we say, by the way, where's clockwise? We definitely need counterclockwise. So what I wanted to try is, I don't even know. Ah, yeah, two. Let's say we only have 2 instances per batch. Let's say if, let's check if resizing works. Oh, what's destroy? Validation error, which is in an invalid state because of the following objects bound to the, okay, in the recording state. So VK begin command buffer. Okay, and so for some reason, it wasn't in the recording state. Okay, so what we probably want to do is actually not destroy the buffer mid-frame. We want to do that after we wait for the fences. So let's go into here and say something like, wait, what do we need for the destruct? Because then we cannot do this, can just do that. So we need a chat GPU buffer pointer. So chat GPU buffer pointer, buffers that need resize. Let's have her frame 32. And then resize GPU buffers just says need UN32T chat GPU n buffers that need resize. And here we just say in this just say context.n buffer that need resizing. Or we could even just have the entire thing be context.buffers that need resizing at context buffer need resizing class equal to buffer. And then we want this, put it at the end of the frame at wait for fences. After that we say if for UN3 arrow as this context or buffer resizing class says yeah, we can say type def struct buffer resize op, and it just has a chat of course chat buffer and a size and this is a chat buffer resize operation and equal to dot buffer equal to that and dot new size chat. This is yes, this 8 this is going to be chat buffer resize op to context of buffer I, and then we do op dot size op buff usage op buff member op buff and op probably put that in. Okay, so let's see if that's working now. Wait, so that is currently in use by command buffer, but we do end command man and begin command buffer. I mean, we reset the command pool, so I definitely need to do this problem. But is resize that even exit? I mean, it probably is. Why did it not yet work? He offsets. Okay, so I finally fixed the issue with the validation layers. Now it works. I needed to change some things up, but not really going to get into the details because we need to create texture. Okay, first we need to create the shader changes. So yeah, let's do that. So basically, let me think. We will definitely need a vert UV per vertex. This is going to be 1, and this is then going to be 2, 3, 4, and then we need to say 1 out vec2 VUV, and then we say VUV equal to AUV, what vert UV, and then in the fragment shader we say we want a descriptor set binding. So descriptor set will be 0, binding will be 0, and uniform sampler it will be taken like that. And then we say, wait, fragment shader never set assignment. Oh, I don't know. Texture with hex and VUV, and we say something like in vec2 VUV, and then we say VUV times V color that. Okay, then we're going to go into the vertex. Where's the overt here? Vec UV, and then the vertices for the quad will have to change. We'll have to say something like like, let's just remove pos entirely, because then we can do it like that. Everyone knows what we mean. And this. So this will be basically the same. So 0, 0, 1, 0, 1, 1. Okay, like that. Then we will need a chat texture, which is going to store the texture actually. So it's going to have a VK image, a VK image view, a VK sampler, and a VMA allocation alloc. So we're going to use VMA to allocate the image, and this is basically everything a image needs in Vulkan, like Pangea texture basically, but this is this. Yeah, and it's a chat texture. Then probably in our pipeline somewhere, let's create our descriptor set. So let's go into here. VK descriptor, and basically descriptor set is just like the image sampling foundation that we just need to manually create. Binding is 0, and descriptor type is equal to VK descriptor type combined image sampler, and descriptor count will be 1. Stage flags is VK shader stage fragment, but VK descriptor set layout create info for the layout info, and I think we just need to specify the bindings. So the redefinition descriptor layout info, descriptor, I really know how to write that, I think like this, is equal to and binding. Binding count will be 1, S type will be VK, structure type, descriptor, set layout, create, well. And then we have VK create descriptor set layout, context, logical device, create info will be the descriptor layout info, null allocator, and the set layout will be VK descriptor set layout. So put that into our context, VK descriptor set context. Okay, we actually have to put that into, where do we create the pipeline layout? Layout here. So we put that in front of here, because the pipeline layout takes in the descriptor set. Where is the pipeline layout? Layout info. We say p set layout is equal to and context.set layout, and p and set layout count 1. Okay, then we actually need the descriptor pool, which is basically the pool of textures. We can specify how many textures we want, stuff like that. So create descriptor pool, context, logical device, create info will be VK descriptor pool create info, pool info, and it will say S type is equal to VK structure type descriptor pool create info, and then we can specify max sets 16. Pool sizes is, I think VK descriptor pool size, and I think the thing is that we can also just say something like size equal to type descriptor count. So descriptor count just 16. Type is VK descriptor type combined image sampler. Descriptor type combined image sampler. And pool size is just going to be size, and pool size count going to be 1. Yeah, and that's that. And then we can just say pool info null for the allocator. Descriptor pool is going to be context dot descriptor pool. So let's have that. VK descriptor pool context dot descriptor pool. Yeah, and then we can actually create the sampler. We're going to use SCB image to sample a texture. So let's get that. SCB image today. You profile. Going to move download slash cb image.h to dev slash Vulkan chat slash just here, and then we'll say hash define scb image implementation hash include cb image.h. Okay, nice. So let's make a function that just loads a text chat texture. So void load texture. I'm going to take in a chat context, a const char pointer path, and a file path, and a chat texture text. Okay, so let's do stbi load file path vi load file. Okay, so we give it int with hide channels, and we want 4, right? And yeah, then we should say something like vk device size text size in bytes going to be width times height times 4, and then let's make a chat. Let's make a vk. So, and then basically we want to vma create image, right? And it's going to take in context.vma and the image create info. So let's have vk image create info image, and then we have s type is equal to vk structure type image create info. Image type is vk image type type 2D, and array layers 1, mid levels is 1, samples is vk sample count 1, usage is vk image usage sampled, right? And I think also vk image usage transfer dest bit. I think that's the most optimized usage transfer, because this is also like done in the VMA example, and I think it's very optimized. Tiling is via image tiling optimal. Makes sense. And yeah, then we have extend, which is a 3D extend, so with height 1. Format, VK format, R8, G8, V8, A8, right? And I think, do we have anything else that we actually need? I think S type, right? VK, no, we already have, right? So I think that's it. Okay, so then we just need a VMA allocation create info, VMA alloc equal to dot usage equal to VMA memory usage. We are going to be cool and say GPU only, right? Because we're cool like that and efficient. Image, and the actual image that we want to allocate or create is o texture.image. The allocation will be o texture.alloc, and this will be no, we had earlier. Okay, so I just pasted in a very handy function from my other project, CoreRender, and it's basically a function to upload. Let's have a underscore in here. So I just pasted in a function from my other project called CoreRender, which just creates a staging buffer in which to put the image data, and then just, it's like not really concurrent or asynchronous, but it's just submitting instantly to the queue, and yeah, basically uploading the buffer to the Vulkan image. And this is the very important function that we will need in here. So then we can just say upload to image context. This is going to be o texture.image. The pixels is going to be unsigned char pointer pixels equal to pixels with height, and this is going to be like that. So now we actually uploaded into Vulkan the image data, and then we can free the CPU side pixels. What's your problem here? Allocator. Forgot to specify the VMA alloc, right? Now we just have to create the image view for the sampler. So now we just have to create the image view on the sampler. So image view create info. I mean, we already have that somewhere. View create info. So let's just have that, and let's have image be the texture image, o texture.image. Format be the format that we specified. View type is still that. Sub resource range is still the same, and then we can just say vk create image view, basically create image view, that. And then we want to create a sampler. Vk sampler create info, sampler info is equal to .s type, vk structure type sampler, and mag filter is vk filter, let's say linear. Min filter is vk filter linear. So basically like the like I think part of creating textures in OpenGL, also kind of like that. Yeah, then we have address mode u, v, and w, and we just put all of them into sampler mode. Sampler address mode repeats u, v, w. It's basically repeating the texture at the corners, and then we vk create sampler context.logical device and sampler info no and o texture dot sampler. I just noticed that I actually forgot something. In chat texture we don't even have a descriptor set for the texture, so we need a vk descriptor set. Your problem now? I just returned to where that wasn't the case. Binding. I guess I actually forgot that we don't have a vk descriptor set for per texture, right? So that's that. We need a descriptor set for each texture, meaning that in load texture now, but no, I use it. So load texture will actually create the descriptor set. So vk allocates descriptor sets, the function. It takes in the logical device and allocate info, vk descriptor set allocate alloc info dot s type is vk structure descriptor set info dot descriptor pool is going to be the context descriptor pool dot descriptor set count will be 1 dot s type dot count set layout will be context dot equal to context dot set, and then we we have the descriptor set with the logical device, the alloc info, and the what does it even take on descriptor? So the and texture dot desk set. Okay, and then we need to update the descriptor sets on the Vulkan logical device. So update descriptor set takes in the logical device. Descriptor write count will be 1, and the descriptor we want to write is vk write descriptor set. Descriptor set write is equal to dot s type is vk structure type write descriptor set dot dest set is equal to text equal to texture dot desk set, and destination binding is going to be 0 as we have in the later, I guess. And then I think we just need to have the type, which is script my image sampler, and then kind of the image info, I guess. vk descriptor image info, and I think it's going to tell the descriptor all of the things about the image. Yeah, image view is equal to text texture dot view. Sampler is going to be texture dot sampler. Image layout is going to be vk image layout shader read only optimal. We want only the best. And the image info is then going to be image info. And then we have the descriptor count. Yeah, and that's basically that. And then we say write descriptor copy count will be 0. Descriptor copies, we don't have any with copy. Okay, so now drawing a texture is very simple in Vulkan actually, because we can just have draw a texture. We just need to bind the descriptor set of the texture that we pass. Meaning, let's say float x, float y, float width, float height, float r, float g, float b, and chat texture text. And then we can just say vk command bind descriptor sets frame dot frame dot command buffer vk pipeline bind point graphics layout is going to be the what layout pipeline layout first set 0 descriptor set count 1 and texture dot descriptor set dynamic offset count get 0 dynamic offset 0. Okay, and then we just draw the rect. That's the cool part. Then we can just draw the rect with x y width height r g e a, because in the shader it's going to check. All right, you have an you actually have a descriptor set bound. Okay, I'm going to use that, man, to use that. So let's say we just say something like in here chat texture text, and then load texture and context, and then let's have Giga-Chad JPEG in home dev Vulkan chat.jpg, and text will be the texture, and then we'll just draw texture passing float. Okay, so texture. Okay, I mean it will not work, but let's see. Let's first try rendering one. Okay. Okay. So we didn't change the vertex attributes correctly. Let's say in chat.c vertex attribute. Okay, so we have 0. Then we want location binding location 1 chat vertex. This is going to be uv, and this is our vertex, and then we have location 2, location 3, location 4, location 5, and 0 1 2 3 4. So we have 0 1 2 3 4, and then we have 5, and that's that. So let's have 5, right? 5. Okay. Create info binding does not exist in binding is 1. This is 0, this is 1, this is 2, this is 3, this is 4. Okay. I mean, I do see something, man. What if we make it a little bit bigger and say we just want it to be white? Oh my fucking god, do you see that? Yo! Wait, let's have this. Let's be at 10,000 Giga-Chads, man. 10,000. I don't care. Oh my god, man. Do you see how beautiful he is? Do you see how beautiful this is, man? Okay, but I think the RGB thing is kind of not... I'm kind of not a fan. Let's try on having the Giga-Chad in its old nice look. Oh my god, it's so perfect. He is so perfect. This is exactly what I wanted to create today. But that's not exactly what I wanted to create today, because actually, that's just 10,000. 100,000. What about 100,000? Oh, okay. I mean, I can see him better now. You know what I mean? Damn. 1 million Giga-Chads. Can't we just bind the descriptor set once? Yeah, whatever. Just do that. What you are seeing is 1 million Giga-Chads. Okay? Okay, so what I just did is kind of make the performance a little bit better. Okay, guys, so I actually messed around a bit in the shader. Look at this. This is legitimately 1 million Giga-Chads. Oh my